So we are going to get started today looking at the next thing. The next thing is equilibrium, chapter 14. And so what we really need to start with and kind of focus on is just giving ourselves a good definition of what equilibrium is in the first place. And so we're going to start with kind of a generic definition of that. And it is this: equilibrium is a state of balance inside of a chemical system. Now, when we think of equilibrium, there are two different types that we can kind of hang on. One of them is one that we're pretty familiar with: static equilibrium. The idea that an object is at rest and stays at rest. So if I've got an object balanced, whether it's a teeter-totter or a piece of paper, a pizza, whatever the case may be, if it is in balance and is at rest, is not moving, then it is in a state of static equilibrium. There is also, however, something called a dynamic equilibrium. And in a dynamic equilibrium, we are still in a state of balance, but we are no longer in a state of rest. And so in a dynamic equilibrium, things are continuing to move behind the scenes. But to the casual observer, it appears like nothing is happening. And it's that version of equilibrium that when we refer to chemical equilibrium, that's what we're thinking of. We're thinking of a dynamic state in motion, but it's happening at the same time. And to the casual observer, if you were just looking at the reaction system, it would appear that nothing is changing. So what we get in these kinds of situations are chemical processes that are reversible, opposing each other, yet happening at equal rates. So, for example, I've got this reaction between dinitrogen tetroxide, which is a colorless gas, and nitrogen dioxide, which is a brown gas. Now, there are two reactions that are happening at the same time in these reactions. One of these reactions is what we would have called the chemical reaction up until about 5 minutes ago. It would have been the dinitrogen tetroxide decomposing into nitrogen dioxide. But since we've introduced this idea of a reversible reaction, this double-headed arrow tells us that while this reaction is ongoing, the reverse reaction is also ongoing as well. And so if I were looking at this reaction system inside of a flask, I really wouldn't note any difference between the two. I wouldn't be going, oh, it's very clear. I can see that the brown gas is turning colorless right now, or that the colorless gas is turning brown. It wouldn't appear that way to us, because if it's at a dynamic equilibrium state, it doesn't show off. It looks the same always. That is, unless we introduce some kind of factor that's going to change it for us in that way. So here's what I want you to do. We just established two different reactions in the previous slide. The conversion of N2O4 to NO2 and the conversion of NO2 to N2O4. So what I want you to do, write the rate laws, assuming these are elementary reactions, write the rate law for the N2O4 conversion, which we will call forward, and for the NO2 reaction, which we will call reverse. So just write that out on a piece of paper somewhere. In top hat, what I want you to do, tell me what the relationship is between those two rates. Okay, so we're seeing mostly the same idea, mostly the same answer here. Talking about an inverse relationship. What do we mean by an inverse relationship? Go ahead. Okay, is that what we're all talking about when we say inversed? Because that's the definition of an inverse relationship. I want to make sure that's what we actually mean. Okay, so since this is a dynamic equilibrium, the rates have to be equal to each other. And the reason we would say they have to be equal to each other is because if they're not equal and opposite, we would notice a change in the system as we observed it. So think about that reaction from brown to colorless. If the two reactions are not equal to each other in rate, we would notice sitting there over time that the reaction mixture either gets darker or it would get lighter depending upon which reaction was faster. But that's not the case here. Now, as far as each one's concerned, the forward reaction, it would be first order in N2O4. The reverse reaction would be second order in NO2. Why these values? Well, because these are elementary reactions. Remember, elementary reactions are ones that are single step mechanisms. So the stoichiometry and the rate law match. And if the forward is equal to the reverse in terms of rate, what this is going to present to us is actually a really interesting finding. So we just summarized everything that we were looking at there. Let's take it one little bit further. If I rearrange these, so coming back here, we've set them equal to each other. If I rearrange this equation so that all of the K's are on one side and all of the concentrations are on the other, what I would get is KF over KR. So I'm dividing each side by KR and each side by the dinitrogen tetroxide. would be equal to the concentration of nitrogen dioxide squared over the concentration of the dinitrogen tetroxide. And if we look at it this way, this combination of constants, Kf over Kr, we're going to rename it. We're going to rename it to capital K, and we're going to call it the equilibrium constant. So why can we do this? Because again, it's a state of equilibrium, which means that if the rates are equal to each other, then the concentrations will not change if we are at equilibrium. So what we would have is a constant forward and a constant reverse rate, which we can term as the equilibrium constant, capital K. And these values, if we are at equilibrium for the concentrations, would also maintain a constant value, which means that we can measure them at that moment in time and establish what the relationship is. So the big thing that we have to walk away with when we are looking at this kind of reversible system is the fact that just because we have an equal rate doesn't mean we're going to have an equal rate constant. It is still possible that one reaction is naturally more inclined to happen than the other one is. And that's going to skew the position of our value K. So just because the rates are the same, that doesn't mean that the concentrations in the reactants and the products are going to be equal to each other. There is still possibility for preference, the forward reaction being more favored than the reverse reaction. If that's the case, Kf is going to be bigger than Kr. Our value for the constant K is going to be large. Up until this point, we've called that a product favored reaction. And that's what we'll call it here as well, where we can see that the results of this chemical reaction are generating a lot of product at a high yield. It's also possible that it goes the other way. We've talked about this to a lesser degree with weak acids and weak bases, and we'll cover those in far greater detail later on this week when we start to look at equilibrium applications of acid-base chemistry. That's a topic for later on this week, though. Right now, we're going to focus on just equilibrium as a general construct and concept. How does this look in real time? Well, let's just say that we're looking at a reaction like this, where I've got hydrogen and carbon dioxide reacting to make water and carbon monoxide. That's the forward reaction. Now, what's interesting about this, if I look at my graphs here, I'm actually starting with the opposite. I'm starting with the products. I've got water vapor and carbon monoxide in high concentration at the beginning of this reaction. As the reaction proceeds, the carbon monoxide and water are going to turn into hydrogen and carbon dioxide. Now, if this was the kinetics chapter, we could monitor and discuss the rates of appearance and disappearance of those reactants and products over time. We're starting to move away from that idea. What we're getting into now more is, okay, as this reaction proceeds, we're going to see that the concentration is going to decrease, but at some point, that concentration of those products is going to level off and maintain a constant value. And for the reactants here, the hydrogen and carbon dioxide, as the products react and form these reactants, their concentration is going to go up. And it's going to increase until it hits some sort of point where it levels off as well. Now, before this time, we would have said, we would have marked this time right here and said, okay, this is the end of the reaction. After all, at this point in time, the concentrations cease changing. And so we have marked that and said, okay, well, that's where the reaction's over. Truth of reality is a chemical reaction is never truly over or done reacting. All that happens is that it hits an equilibrium state. And in that equilibrium state, we no longer notice that the reaction has continued. It has started to reverse itself, and now it has hit this dynamic equilibrium condition at whatever time value that is. So we no longer consider an end of reaction. We just consider what is our equilibrium condition. And that's what we end up investigating, especially for these reactions where there is a good bit of reversibility, where it isn't like a 97-3 kind of situation where we get 97% product and only 3% unreacted stuff at that equilibrium point. Looking at this again from a standpoint of rate, we can monitor the forward rate of reaction and the reverse rate of reaction, understanding that at some point those two roads will converge. And when those two rates converge, that is our equilibrium state. And the forward rate is truly equal to the reverse rate there. Up until that point, we know that that is definitely not the case. So, if we look at this kind of information here, T equals 0 kinds of rates of reaction, that's exactly what we were studying last week. Studies of kinetics generally talk about what we're doing at the very beginning of the reaction, prior to equilibrium. So we can see what we were talking about last week does have a direct connection to what we're talking about now and what we'll be talking about for the next couple of weeks. It's just looking at two different pieces of time for the chemical timeline. When we want to look at the kinetics of a reaction, we're looking at the initial part of the reaction, right when we mix that stuff together. When we're investigating equilibrium, we're looking at largely when the reaction has ceased changing. And we're either going to look at how it changes when we manipulate the system, change its parameters, change its temperature, change its volume, add something to it, or we're investigating a particular type of chemical reaction that has specific ramifications to it. So we will be here in equilibrium. Some of you might call it equilibrium hell for a while. In a normal semester, it's about 5-6 weeks. For us, it'll be about a week and a half, maybe 2 weeks. But the good thing about that is, again, we can tie it back to where we were before. We know that we're looking at the same chemical reaction. We're just looking at it from a different time stamp. Instead of time equals 0, we're talking about time is equal to E. Time is equal to infinity. The other thing that we're looking at is, because there is so many applications, once we start to understand the kind of nuts and bolts of how to handle these systems, it's just going to be a matter of taking the core principle and turning it 30 degrees to look at it from a new perspective. So as we go from this chapter to chapter 15 to chapter 16, I want you to keep that in mind. The focus is going to be the same in all 3 of these chapters. It's just, how are we turning that lens to look at it from a new perspective for a new situation? So let's get some of our basics down. What is it that the equilibrium constant tells us? First of all, it does tell us the position of the chemical reaction in terms of where is it favoring in terms of products or reactants. If our K value is large, greater than 1, significantly greater than 1, we will talk about this as a product favored reaction. That means that the forward reaction is more favorable in some way than the reverse reaction is. And as a result, if I look at that mixture of reactants and products at that equilibrium point, I'm going to see that there is way more product than reactant. If my K value is small, less than 1, significantly less than 1, getting into those negative exponents, which again, looking ahead, chapters 15 and 16 focus largely on those negative exponents. That indicates that the system favors the reactants. So the equilibrium system in question is going to have far more reactants that did not convert than product that did. What the constant can't do, however, and we've got to make sure that we have this straight, this is a departure from kinetics. The constant, equilibrium constant, capital K, can't tell us the rate of reaction. Again, it's not concerned with the rate of reaction. It's concerned about when those rates are equal to each other, where is the reaction system? Again, kinetics and equilibrium are looking at the same reaction system at 2 very different times. Kinetics focuses on the initial condition. Equilibrium focuses on the end condition. We can estimate the value of the equilibrium constant using something called the law of mass action. The law of mass action in particular gives us the relationship between the equilibrium concentration of the reactants and products and the stoichiometry of the equation that they come from. And the calculation is always this. It is the concentration of the products divided by the concentration of the reactants. And notice here, the values of the exponents are, in fact, directly related, equal to the values of the stoichiometric coefficients from that balanced equilibrium equation. So unlike in kinetics, where we had to be very concerned about the rate determining step and making sure that the rate law matched up correctly with that mechanism, knowing that molecularity was an issue, knowing that stoichiometry didn't necessarily dictate rate law, all that stuff that we had to be really careful about with kinetics, we don't have to be careful with here. Here, the coefficients are the exponents. So we just move them appropriately. Concentration of products divided by concentration of reactants, each to their appropriate exponents. So we're going to start with the most common version of the equilibrium constant. This is K sub C, or Kc. Most of the time when someone refers to the equilibrium constant, this is what they are referring to. And it is the concentration-based version of the equilibrium constant. So I take the concentrations of the products, divide them by the concentrations of the reactants. Some important things to know, though. We're going to reinforce this when we talk about heterogeneous equilibrium, but it's worth saying first time now. In order to be included in the equilibrium expression, we have to have something that we can actually calculate the concentration of. So it needs to be either in the aqueous phase, a solution, or in the gas phase. Pure liquids, not included. Pure solids, not included. Any guesses as to why? Okay. One of the things you said was accurate. It's not about neutralization. It is about changing, though. Trayton, you got something? Okay, that has part to do with it. Any other ideas? So it does have to do with a lack of changing. Pure liquids and pure solids are not going to really have concentrations at all, right? They're pure. And if I have a pure solid, that means it's undissolved. If I put that pure solid into a solution, it's not going to dissolve in the solution. Otherwise, it would be considered aqueous as well, right? So how do I measure its concentration? I can't just look at its density. Its density is going to be unchanging. I can't look at it in terms of the context of the total solution because it's not in the whole solution. It doesn't have that much volume. It's going to settle to the bottom. Even if I mix it around really, really, really good, it's still not going to take up the entirety of space. So how do I measure its concentration in a way that can be useful to this expression? The answer is I can't. The other thing that we have to consider is that in it that way, its concentration isn't going to change. And so if its concentration isn't going to change, regardless of what we do to the system, then it really doesn't belong in the equilibrium concentration part. It belongs on the other side with the other constants. That's more or less what happens. Same thing with pure liquids. If I look at water, yes, I can say, okay, water is a product of this reaction. It's a pure liquid. It's going to take up the entire space because it's a solvent and it is the solvent. Does anyone know the concentration of water in itself? You can actually do the math on this. It's about 56 molar. What are the odds that I'm going to have anything else concentrated enough in that water to make the water's concentration change significantly upon reaction? So it's the same kind of argument. The concentration is not going to change, even if we change the reaction conditions around it. And so since it's unchanging, it's a constant. It's on the other side of the expression with the other constants as well. So we'll get more into this when we talk about heterogeneous equilibria, where we've got more than one phase present and how we kind of rationalize that and deal with that. But just kind of keep that in mind. If I'm building these expressions, I need to think about things that are actually measurable in terms of their concentration. And so that's why we look at aqueous solutions, because we can measure them very precisely, moles per liter. We know exactly how much solution there is. We know exactly how much of that substance is dissolved in that solution. For gases, same thing. Now, we're not looking at the solution, but we are looking at the container itself. We can measure the total volume of the container and how much of that gas is in the container. So that's a concentration. Moles per liter, just the same. Now, Kc is the most common version of the equilibrium constant, but it's not the only one. There are others. Another common one is Kp. Kp we will find when we are dealing with reactions that are exclusively in the gas phase. So if I have a reaction where all of the substances in the reaction are gases, oftentimes it is easier to measure the pressures of those gases rather than trying to figure out their concentrations. And so all that really changes is, instead of concentrations here, we're doing P. P is the partial pressure of each one of these substances. But notice the same rules still apply to Kp as did to KC. The coefficients in the balanced equation turn into exponents in the equilibrium expression. Now, there is a relationship between KP and KC. We can find this relationship by doing a slight manipulation of the ideal gas law. We won't get into the derivation of it. But what it comes down to is this. If I know the value of KC, I can turn it into KP by taking that value of KC and multiplying it by the quantity R, the universal gas constant, times T, the Kelvin temperature, raised to the power of delta N. Delta N being the relationship between the number of gas molecules in the products versus the number of gas molecules in the reactants. Now, a couple of important things to know about R and T here. R has to be the value for atmospheres. Atmospheres is the unofficial pressure unit of equilibrium. It's not written down anywhere in stone. I've never seen it actually verified that that's what it has to be. Like, no reference text says so. But every single example I've ever encountered has used atmospheres for the pressure unit and 0.08206 as the value of R. Temperature has to be in Kelvin. Cannot be in Celsius, cannot be in Fahrenheit. One other important thing of note, if the number of gas molecules is equal on both sides, KC and KP are the same. Because if the number of gas molecules is equal on both sides, that means delta N is equal to 0. RT to the 0th power, it would be equal to 1. So in those cases, it would be somewhat of a easy conversion, kind of a moot point. Just keep in mind, if delta N is a negative value, remember, negative means reciprocal. So what you're going to do, instead of multiplying by RT to the N, you would divide by RT to the N if it ended up being negative. That's really the only difference. All right, let's take a look at an example here. We've got a reaction that is key to the formation of acid rain. Sulfur dioxide reacting with oxygen to make sulfur trioxide. What we're asked to do here is to determine what KC and KP are in terms of expression. So for KC, again, we're looking at the concentration of products over the concentration of reactants. So the product here, there's only one, it's sulfur trioxide. And it would be squared because the coefficient is 2. For the reactants, I've got sulfur dioxide, SO2, and oxygen, O2. Coefficient for sulfur dioxide would also give us a squaring for the sulfur dioxide in our K expression. Oxygen is just 1, so we'll leave it as it is right there. So there is my expression for KC. Now for KP, pretty much the same thing, only it's the partial pressure of the products over the partial pressure of the reactants. So it would be the partial pressure of sulfur trioxide squared over the partial pressure of sulfur dioxide squared multiplied by the partial pressure of oxygen. Right. Any questions with this one? All right, let's do a calculation then. We've got a chamber that contains both nitrogen dioxide and dinitrogen tetroxide. The partial pressures are 0.34 atmospheres and 0.8 atmospheres. What is the value of Kp at these conditions? So looking at the equilibrium expression as it is written right here, I know that Kp is going to be equal to the pressure of N2O4 over the pressure of NO2 quantity squared. We are told that the pressure of N2O4 is 0.80 atmospheres. We are told that the pressure of NO2 is 0.34 atmospheres. And since we are going to need to square that, .80 divided by 0.34 squared to two significant figures is going to give us a value of 6.9 as the value of Kp. Now, equilibrium has one really nice thing that's going for it. The values of K do not have units attached to them. So unlike the rate constants where we had to, make sure, okay, molar to the -2, seconds to the -1, all that stuff that we had to do for the rate constants does not apply here for the equilibrium constants. You don't have to worry about those. So we can consider the values of the equilibrium constant to be unitless. And so that's where we'll take that discussion. So 6.9 is a perfectly valid answer for that expression there. What it tells us is that this reaction is slightly tilted toward the products. And N2O4 is slightly more favorable than the NO2 is, at least at this condition, this temperature. All right, any questions here? All right, let's look at another one. Determine the equilibrium expression for the following reaction. Determine the value of Kc and Kp at 25 Celsius if the substances have the following concentrations at equilibrium. So for the equilibrium expression, K is going to be equal to the concentration of carbonyl chloride, COCl2, divided by the concentration of carbon monoxide multiplied by the concentration of the chlorine. Now, the reason I did concentrations here, the reason we're going to solve Kc is because the values that we've been given are concentrations and not pressures. If we were given partial pressure values, we solve Kp first and then convert it. Substituting in our concentrations, 1.47 times 10 to the negative second for the carbonyl chloride, divided by 1.8 times 10 to the negative sixth, and 1.8 times 10 to the negative sixth again. 1.47 times 10 to the negative second divided by 1.8 times 10 to the negative 6 squared to two significant figures is going to give us a pretty big value here, 4.5 times 10 to the ninth. So I think it goes without saying here that this is a product favored reaction. Very, very, very skewed toward that product side. And the concentrations definitely reflect that. There's a 1,000-fold there's a 10,000-fold difference in their equilibrium concentrations nearly. Now to convert it to Kp, we've got to use that other expression. Kp is equal to Kc times RT to the delta N. Now the value of Kc we just calculated, 4.5 times 10 to the ninth. Value of R is 0.08206. T needs to be Kelvin, 225 Celsius is 298 Kelvin. And delta N would be gas products, 1, minus gas reactants, 2. So 1 minus 2 gives us -1, which means that this is going to be the denominator, not the numerator. 4.5 times 10 to the ninth over 0.08206 times 298. Our Kp value (1.9 times 10 to the 8th). Why such a difference? Well, that loss of gas molecule is going to have some impact. All right, any questions with this exercise? All right, so I'm going to invite you to do some of this on your own here. So we've got a different reaction between carbon monoxide and hydrogen to make methanol. I want you to determine the value of Kc if the equilibrium mixture contains that mix of stuff in a 2-liter vessel. And I want you to do the KP as well. One important thing to keep in mind, these are not concentration values. These are mole values. You're going to have to convert them into molarities first. And since this is a 2-liter vessel, they are not going to be the same. So just kind of keep that in mind as you go and do the calculation here. Once you've put your answer in, go ahead and get up and stretch, take a little bit of a break. We will come back to this in roughly, let's say half past. So take what time you need to do it. Use the remaining time, just kind of stretch out and get loose. And we'll come back and talk about it in about a little bit more than 10 minutes. All right, let's see how we did. So let's start with kind of the easy stuff here. We need to convert all of these moles into molarities. Since it's moles per liter, we're doing moles divided by 2 liters. So 0.0406 is going to become 0.0203 molar methanol. 0.17 is going to become 0.0850 molar carbon monoxide. 0.302 moles would become 0.151 molar hydrogen. So for KC, we would need the concentration of the methanol divided by the concentration of the carbon monoxide divided by the concentration of the hydrogen, quantity squared. So with those numbers now, it's 0.0203 molar over 0.0850 molar multiplied by 0.151 molar quantity squared. So 0.0203 divided by 0.085 divided by 0.151 squared to 3 significant figures. We would get a value of KC at 10.5. And again, it's an equilibrium constant, so it has no unit. Just leave it as it is. Now for KP, we're told we're at 500 Kelvin, so there's our temperature. KP is equal to KC times RT delta N. So 10.5 times the quantity of 0.08206 times 500 . This time, I have 1 product gas and 3 reactant gases. So my exponent here is not -1 this time, it's actually -2. So KP is going to be equal to 10.5 over the quantity 0.08206 times 500 squared. So 10.5 divided by 0.08206 times 500 quantity squared. Do 3 significant figures again. 6.24 times 10 to the -3rd. And so we're going to always find that this is the case. If our forward reaction is generating fewer gas molecules than what were in our reactants, Kp is going to go down relative to Kc. If we find that we have more gas product, Kp is going to go up accordingly. If they are equal, just remember that that means that Kc and Kp are equal also. Any questions with this example? All right, so we just have a couple of last things to cover for today, and then we'll call it a day as far as our first day of equilibrium is concerned. And what we're going to look at is how can we manipulate K to other situations? So what if we knew the value of K in one direction, but we decided to flip that equilibrium around? How would that impact our results? Well, it's actually not that tough, because since we are dealing with a reaction that has a very prescribed method to it, all that we really have to do is look at how is our new version of K related to the old version of K. So we can kind of think about it this way. If I've got this equilibrium expression, A turns into B, I know that for K as it is currently written, it'd be the concentration of B over the concentration of A. But if I decided to flip it around and look at B in equilibrium with A, well, all I would need to do is flip around the expression as well. The relationship between the blue K and the orange K is that they're reciprocals of each other. Reciprocals can be reflected using the -1 power. So if I know that the blue reaction has a value of 10, then that means that the orange reaction is 1 over 10. It's just the flip of it. Similarly, if I multiply a reaction by a coefficient, it gets reflected in the value of the K as well. Not as a multiplier, but as an exponent. So again, the way to look at this, let's just do a little comparison. The K expression for this first reaction would be NO2 quantity squared over N2O4. If I compare it to the bottom reaction, it would be NO2 to the fourth over N2O4 quantity squared. Just looking at the exponents here, I can establish that the orange K is equal to the blue K squared. I just took this whole thing and squared it. And so if I know that the value is 0.212 for the blue, well, 0.212 squared, 0.0449, would be the value for the orange. So any manipulation that we do to an equilibrium expression, whether it's by accident or by design, if we know the value at one of those conditions, we can work back to figure out the value of the equilibrium expression at the other set of conditions. We don't have to go through a large process of looking at, okay, well, what are the equilibrium concentrations here versus here? What is it going to do in this situation or that situation? Do I just need to run the experiment again? None of that stuff matters. If I know the value of K for a given expression, and I can see that this other expression is just a manipulation of the first, I just need to apply the same manipulation to the constant as well. All right, this is not a top hat question. We've already done the proof for number one. Actually, we did the proof for number two as well. I kind of spoiled that, didn't I? Does anyone have any questions about where those numbers come from? Obviously, I didn't intend to solve that on the previous slide. My mistake is your gain. Where this can be useful is in situations like this. Let's say that we have a mechanism. And I know the equilibrium constant for the first leg of the mechanism. I know the equilibrium constant for the second leg of the mechanism. I want to know the overall equilibrium constant. How can I find it? Well, we can do the same kind of things. Let's figure out what the equilibrium expression is for this one, and let's see how it is related to the other two. So Kc3 should be equal to the concentration of nitrogen monoxide squared multiplied by the concentration of bromochloride squared over the concentration of nitrous bromide squared and the concentration of chlorine, not squared. Now, one other thing that I can look at here is how did I get from 3 based on 1 and 2? And I can see that if I add together the equations, I did just that. Well, maybe the same kind of thing needs to apply here as well. Instead of adding the equations together, because we haven't added a single thing today, what if we multiplied them? So if I take these two and multiply them by each other, so I've got bromochloride squared here, I've got bromine and chlorine there. I can see that if I multiply these together, the bromines would cancel out. And what I would be left with is the exact expression that the sum, if I was just doing the equilibrium expression without the prior context, that's exactly what the expression we would have anticipated would be. And so that's the other manipulation that we can do. If we're adding together reaction steps, we can multiply their equilibrium constants by each other to get the equilibrium constant of whatever that summary reaction is. So again, where this is particularly useful is things like mechanisms, where I've got a series of reaction steps that need to take place. I know all of the data about the individual steps. I can multiply those values together to give me the equilibrium constant of that composite overall net reaction. So let's look at a question like this then. At 1000 degrees, the Kc values for the following reactions are given as follows. What is the Kc value at 1000 Kelvin for this reaction? So this is not as easy as just adding together those two equations and getting to the end result. If I add these two equations together, what I end up getting is N2O4 plus N2 and O2 O2s give 4 NO2s. That's not the reaction I'm looking for. The reaction I'm looking for actually doesn't have NO2 in it at all. So what I need to do is I need to manipulate these equations accordingly to get rid of the NO2, which isn't even in the expression to begin with, and give me the product I'm interested in the first place. Now, those of you with a little bit of familiarity with thermochemistry, whether from high school or from previous experience in the course, are familiar with the concept of Hess's law. Hess's law being the idea that you can manipulate equations, flip them around, multiply them, turn them inside out to get to an equation that you're ultimately interested in. And that's more or less what we're going to be doing here as well. To get to this expression here, I'm going to need to flip this top equation. To flip this top equation would mean that the nitrogen dioxide is now the forward reaction, and the dinitrogen tetroxide is the reverse. Since I flipped the reaction, I need to flip the equilibrium constant as well. We just talked about that. Now, changing its sign makes no sense whatsoever. Remember, to flip a constant like this, we need to take its reciprocal. 1.5 times 10 to the negative sixth raised to the negative first power, or 1 divided by 1.5 times 10 to the negative sixth, either way you want to look at it. So if I take 1 divided by 1.5 times 10 to the sixth to two significant figures, this comes out as 6.7 times 10 to the negative seventh. So we're going to cross out that version of the equation. And now we're going to add these together and make sure that our NO2s cancel out and that we are getting the version of the equation that we're actually interested in. Which we are. The Kc value for this expression would be equal to Kc for the first reaction multiplied by Kc for the second reaction. So 6.7 times 10 to the negative seventh multiplied by 1.4 times 10 to the negative 10th. So we're going to get ourselves a real small number here. Two significant figures, 9.4 times 10 to the negative 17th. So at 1,000 degrees Kelvin, this is an extremely unfavorable reaction. This is very, 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 very reactant favored. If we were to look at this expression, if we were looking at this mixture, we would see almost exclusively nitrogen and oxygen and very little of the dinitrogen tetroxide. Right. Any questions with manipulating equations to get new values of K?